All right, let's review associations and their analysis. So really the fundamental question in business analytics is typically, is there a relationship between two variables of interest, like how much someone is spending and how far away they live from the store, the probability of responding to a promotion based on how many promotions they're being sent, etc. So the key points that you want to be able to make sure you're comfortable with is talking about what it means for two variables to have an association, what it means when two variables do not, and be able to do all aspects of the analysis of the association, being able to cast the two variables into the roles of y and x based on the context of the problem, being able to visualize and know which plot you need to look at depending on the types of variables involved, if they're categorical or quantitative, and then be able to look at the plots and gauge whether or not there looks to be a strong or interesting association. So know what these plots look like when there is an association going on and what these plots look like when there is not. And then if there does look like there is an association, you need to know how to determine whether or not that association is statistically significant. In other words, is this something that could have been produced by chance alone, or is it more indicative of a real relationship going on between the two variables? And so along with that was the analysis of the p-value, know exactly what the p-value is referring to, be able to interpret what the value of a p-value is actually telling us, and understand what the implications of various sizes of p-values are. So at the end of the day, after the analysis of an association has been done, we'll either conclude that the association has or does not have statistical significance, and whether or not it has practical importance or practical significance to us. So know what the implications are when an association is statistically significant, and also know the implications when the association is not statistically significant. All right, so in order to really get started with the analysis, we know that we have to cast the two variables into the roles of x and y, because all of the equations, all of the visualizations kind of hinge on the variables being assigned to the correct roles. And so the key step in the analysis is to, based on the context of the problem, determine which variable plays which role. Our y variable is really our quantity of interest. It's the quantity that we're really studying or maybe making predictions for. And x is essentially the other quantity. It's the quantity that you're going to use to make those predictions. So there are a few ways to think about it, but typically what I think is, x is the quantity that you already know. It's the information you know about, and y is the quantity that you wish you knew, that you wanted to be making predictions for here. All right, so there's a slide that goes through over a few examples that says, hey, what if you're going to look at an association between sales and advertising? Which roles would be which? Well, one thing that I would know is probably the amount of advertising that a product had, and what I'd like to know is what the sales of that product was. I'd want to use advertising to predict sales, and so based on just the nature of the problem, I would cast my variables as y being sales, which I want to predict, and x be advertising, which I want to be using to make that prediction. Sometimes the analysis can really go either way, like if you were looking at the association between political outlook and whether or not someone had gone Greek. It might be interesting to use whether or not someone did go Greek to predict what their political outlook might be, conservative or liberal. Or it might be interesting to go the other way around. Based on someone's political outlook, using the political outlook as the x variable, can we predict whether or not someone would actually join a fraternity or sorority? So be comfortable with assigning variables into the role of x and y with the context of the problem given to you. It's a very important task. All right, so when we have our two variables, they've been cast in the roles of x and y, what does it even mean for x and y to have an association? So the word association is really a very general term to describe when there's a relationship going on between the two variables, and we think about it in this way. We say that x and y have an association when, for whatever reason, knowing an individual's value of x tells you something about their possible values of y, or in other words, narrow down the possible values of y that they might actually have. And so if that's the case, knowing the individual's x provides you some additional information about what their values of y might be, and that's what we say when we discuss two variables having an association. Now, very often, just in the real world, people use the word correlation to describe a very general relationship, but one key thing in this class is that there is a key difference between two variables having an association and two variables having a correlation. So association is just the name for some sort of general relationship. A correlation is the name for a very specific type of relationship when both x and y are numerical, quantitative variables. And if we made a scatter plot, the relationship between the x and y values of the individuals is well described by a straight line. So correlation we're only going to use when we're talking about relationships between numerical values of x and y, and those two variables have a linear relationship. Okay, so let's start out by reviewing how we go about analyzing associations when both of the variables involved are categorical variables. So what do you need to be able to do? What should we be able to talk about? Well, talk about what the contingency table tells us and also what the relevant visualization is, the mosaic plot. Be able to read off essentially the most frequent or least frequently appearing levels based on either of these two things. And also be able to tell me, how many individuals had this particular level of x, how many individuals had this particular level of y based on the contingency table. And the interpretation of the mosaic plot, the visual interpretation, is extremely important. Be able to determine, just by looking at the mosaic plot alone, whether or not you should suspect that there's an association going on between the two variables, and also be able to at least informally gauge how strong that association might be. And then if we want to investigate further, if we actually want to run a statistical test for the association, you need to know the ins and outs on how that test is actually performed. What exactly is being calculated or compared, and how is the assessment of statistical significance being made? In other words, know how that permutation procedure works. So the end result of a statistical test is a p-value, and we know that we compare that p-value typically to 5% to determine if it is statistically significant or not. And so make sure you know that, hey, a statistically significant association is one where the p-value is less than 5%. And be able to interpret what that p-value is actually telling us, what it's not telling us, etc. So let's go over through some examples. Here's the mosaic plot exploring the association between someone's gender and what class level they were when they took Stat 201. And so what the mosaic plot does is it essentially breaks down the distribution of the y variable, which is the one labeled on the vertical axis, in this case male and female. It breaks down that distribution of y for each level of x, in this case the class level of the individual. And we say there's an association when knowing the individual's value of x narrows down the possible values for that individual's y. And so in this case, the question is saying, okay, if I know what class the individual is, does that give me any additional information about what the gender of the individual might be? So in this case, overall, it looks like slightly more than half of the people in the survey here were female, a little bit less than half were males. And so what we'd like to know is that if we know the individual's class, does that narrow down kind of what the proportion of males and females are? And so what we do is we look and we compare the segmented bar charts, the distribution of y for each level of x, with the overall distribution of y. And then also the segmented bar charts across each other here for each level of x. And the way that we can tell if there's an association is if the segmented bar charts look different as we go from left to right. If they do look different, then the distribution of y is somehow different between the levels of x, indicating that if we do know an individual's value of x, that narrows down the possible values for y that individual might have. So I would say that there is a hint of an association going on between gender and class because, well, for sophomores, it looks like, there's a stronger majority of sophomores that are female compared to the junior class. It looks like actually there might be a slight majority that are male. So knowing the class level kind of tells me something additional about the distribution of gender. I would say there's an association. So what do we need to know about the segmented bar chart? Well, basically each level of x, the x variable here, gets its own segmented bar chart. And what that's doing is it's showing you the distribution of y for that level of x. And the way to read that is to look to see, what areas of the segmented bar chart are devoted to each level of y. The areas are proportional to the percentage of the individuals with that level of y. And so that's really what you're comparing, kind of up and down the overall distribution of y between each level of x here. The different bar widths here don't tell you anything at all. It just tells you something about the relative frequencies of the x variable. Here, seniors are rarer than sophomores. It doesn't comment on any aspect of the relationship. All right, so not only do we use the mosaic plot to gauge whether or not there is or is not an association, but also how strong that association is. The bigger the discrepancy in the segment and bar charts, the stronger that association is, the more narrowed down the possible values of y are based on the individual's level of x. All right, so here's an example of a weak or potentially non-existent relationship because the three levels of handedness, ambidextrous, left, and right, it looks like the distribution of whether or not they have a significant other is essentially the same for all three levels, and it's about the same as the overall distribution of whether or not people have a significant other. So I would say there's a weak, if any, association going on here, but there's a very strong association between the drop call frequency that individual students are experiencing based on their cell phone provider. It looks like they're very different distributions of rarely, often, and occasional, depending on what cell phone provider we're talking about. And so I would suspect a fairly strong association there because there's pretty big and noticeable differences. So when we want to follow this up and determine that there is or is not a statistically significant association, what we need to do is we need to figure out if the observed differences in the segmented bar charts that we're seeing can just be explainable by chance. We're just collecting data, it's a random sample, so we expect there to be some variation. We need to make sure that the variation that we're observing really just can't be readily explainable by just chance variation here. And so what we're going to say is that the association is statistically significant if it's unlikely, in other words, there's less than a 5% chance, that we would actually get a mosaic plot that would exhibit differences in segmented bar charts at least as large as the ones that we actually found in our data, just by random chance. In other words, if x and y were independent of one another. So we need to figure out the p-value of the relationship. Basically, what is the chance that we would observe differences in the segmented bar charts at least as big as what we got from our data if x and y were independent? And so that's where we use the permutation procedure. But just a quick note about this, if we do find that there is a statistically significant association, never does the p-value, never does the fact that a relationship has statistical significance imply anything about the strength or importance of that relationship. So for very large sample sizes, very weak and unimportant associations can be highly statistically significant. So just because you get a p-value that's super, super tiny doesn't mean that that relationship is strong or really of any practical interest to you. The p-value and the strength of the relationship are two different quantities. So statistical significance just means it's unlikely for chance variation to produce differences in the mosaic plot like what you observed, but doesn't say if those differences are large at all. And likewise, if we do not find a statistically significant relationship, that doesn't mean there isn't an association going on. It just means that whatever association exists must be too weak to have been detected from your data, or maybe there's a lurking variable involved that's suppressing the association, leaving you unable to detect it. All right, so what do we actually measure when we're conducting this test? Well, we're not actually looking at the discrepancies in the segmented bar charts themselves. We're actually going to be comparing the observed counts in the contingency table, basically how often we saw each level of x paired with each level of y. We're observing the counts inside the contingency table to the counts we would have expected to have been there if our x and y variables were independent. And so there were some formulas that told us what the expected values were based on the row totals and the column totals of the observed data. We're not going to worry too much about that, but what we end up measuring is the measure of discrepancy between those observed and expected counts. Basically, for every single cell in that contingency table, looking at the square difference between the observed value and the expected value divided by the expected value here. And so our value of D gives us an overall measure of the discrepancy between the data that we've observed and the data we would have expected to have collected had there been no association going on. So larger values of D are progressively more and more evidence that there's an association going on. And so the question becomes how large of a D is indicative of a real association and not something that can be just readily explainable by chance. All right, so what we're going to do is we're going to calculate the p-value of the discrepancy, basically the difference in the observed versus the expected counts in that contingency table. And the p-value is the probability that chance alone could produce a value of D at least as big as the one that we collected in the data. So in other words, if x and y were independent, if knowing an individual's x value told you nothing about the possible y values of that individual, and we collected some data in that case, The p-value is the probability of observing a discrepancy between observed counts in the contingency table and the expected counts, at least, so that a value of d at least as big as what we measured in the data. And so that's when we say if the p-value is less than 5%, it's statistically significant. It's very unlikely that chance alone could have produced a discrepancy at least as big as what we've observed. If that p-value is 5% or greater, we say the association is not statistically significant. We don't need to invoke an association between x and y to explain the differences that we're seeing. That's just readily explainable just by the process of sampling variation. So how can we figure out what values of d happen by chance? How do we get this p-value? Well, we run the permutation procedure. Basically, we take the values of x and y that we've observed, and we create a permutation data set by randomly pairing up the observed values of x and y. By design, in the permutation set, those values of x and y are independent because they were being paired at random. So if we make the contingency table, make the table of expected counts and compare them, and calculate the value of d for that permutation data set, that value of d is one that genuinely has been produced by chance. So we can repeat this process. We can make a ton of permutation data sets and see if the value of d that you measured in your sample is one that can be produced just by chance if x and y were independent of one another. All right, so what we look at in the command associate is the histogram of the chance values in discrepancy, the values of the discrepancy produced over those permutation data sets. So here on the left is an example where the association is not statistically significant because the value of the discrepancy measured in the data, right at about 2.5 here, is a value that happens all the time when x and y have no association, if they're just randomly paired together. So chance alone is enough to explain the discrepancy in the observed and expected counts that I'm seeing, so I would say the association is not statistically significant. On the right here is an example of when I would say we have a statistically significant association. It looks like that the value of the discrepancy that I measured in the data, about 15 here, is way out of line with the values of the discrepancy that arise just by chance when x and y are paired randomly together, when there's no information shared between them. All right, so we get a formal decision by actually taking this information and looking at the p-value. Basically, what were the fraction of the permutation data sets that were able to produce a value of d at least as big as the value observed in your data. So the fraction of permutation data sets whose values of d were to the right of that red line. And so the estimated p-value is here, but since it's just a simulation from maybe 500 permutation data sets, we haven't nailed down the p-value exactly. There's some uncertainty with it. And so we look at the 95% confidence interval for the p-value, and we check to see, well, where is 5%? And if the range of p-values are all less than 5%, then we say it's statistically significant. If the range of p-values is all greater than 5%, we say it's not statistically significant. If we run into a case like this where 5% is right in the middle, well, we're not sure if the p-value is less than 5 or bigger than 5% because there are possibilities on both sides. So we say the test is inconclusive and we need to up the number of permutation data sets to better nail down what that p-value is. All right, so what if one of those variables was quantitative instead? So what do we do in this case when one of the variables is categorical and one of the variables is quantitative? Well, for the sake of this class, we're always going to assume that the y variable is the quantitative numerical variable and our x variable is the categorical variable with levels. So what you need to know is be able to look at the visualization of that association, basically look at the set of side-by-side box plots, and to be able to anticipate whether or not there is or is not an association, and then also gauge approximately how strong or how interesting that association is based on the differences you're seeing. And then based on those side-by-side box plots, and more specifically based on the QQ plot, know what you should be comparing between each level of x. Should you be comparing the average value of y or the median value of y between each level of x? So we don't compare the overall distribution of y values for each level of x. That's too hard of a problem. We just compare the typical value, and the important skill you need to be able to bring to the table is which typical value. Is it the average value or is it the median value? Which one do you pick based on the QQ plot? All right, so once you've determined exactly what we're comparing, I'd like you to understand exactly how that comparison is being made. What exactly is being measured about the typical value of y between each level of x here. No specific formulas, but just kind of in general what's going on behind the test. and then also determine whether or not the association is statistically significant once we've determined exactly what we're measuring, what we're comparing between the levels of x here. All right, so like I said, the analysis of associations here when one variable is categorical, one's quantitative, is only going to focus on whether the average value or the median value of y is different between levels. And so we're actually going to leave ourselves open to missing out on certain types of an association. So I also want you to know what kinds of associations we'll actually be able to detect with the statistical test that we run here, and which associations we're going to miss. All right, so let's actually address that right now. So what we do is, instead of actually checking to see whether or not the entire distribution of y values is the same for each level of x, that's actually tricky, all we do is focus in on the typical value of y for each level, either the average or the median. So how do we determine which one we're comparing? Well, we're going to compare the averages if all the distributions of y for each level of x are roughly symmetric with no extreme outliers, or in other words, if the distribution of y for each level of x is well described by a normal curve. This is why we look at the QQ plot. And if that's the case, we'll compare averages. If it's not the case, we're going to compare medians otherwise. Okay, so when we do that, when we restrict ourselves to that way of analyzing the problem, we're going to be able to detect associations where the different levels of x do differ in their typical values of y. So we'll be able to detect associations that look like this. Imagine we have two levels of x, basically the black group and the red group. Here we see that the typical value for the black group is around 20, the typical value for the red group is around 25. Very different typical values. Our test is going to be able to pick up on that and determine that, hey, there's an association going on. These two groups have different typical values of y. We're going to miss out on associations that look like this. It's very obvious that, okay, knowing which level of x we belong to, if we're in the black or the red group, that does narrow down the possible values of y of the individuals. Basically, if we know we're in the black group, the y values are pretty tightly clustered around 20, whereas if we're in the red group, the y values are pretty diffuse around 20, between 16 and 24. But since we're only comparing the typical values of y, and we actually see that both the red and the black group have typical values right at about 20. So we're going to miss out on detecting these sort of associations. And we're also going to miss out on detecting associations like this. It turns out that both the black group and the red group actually have the same average value for y, just at about 10 here. But obviously knowing which group I belong to does narrow down, does tell me a great deal about the possible values of y that I might observe. If I'm part of the black group, I'm very likely to observe relatively small values of y. If I'm part of the red group, the y values I'm going to observe are probably fairly tightly clustered around 10. So when we do our analysis, we're restricting ourselves to detecting only differences in typical values. We're not going to be able to tell the difference between, say, the typical spread in y values between two groups, or the frequency of low versus medium versus high values. It's only in the typical value themselves. All right, so what's the visualization we make? We look at the side-by-side box plots giving the distribution of y for each level of x. And we're either going to compare the medians, which are given by the horizontal lines through the box plots, or we're going to compare the averages, which are the stars, through the box plots. And what we're looking for is seeing if the typical value is different between each level of x here. And so we just look to see how much of a variation do we see in averages, or how much of a variation do we see in median values. In this case, we're looking at the distribution of height for juniors, for seniors, and for sophomores, and we see that the median values really aren't all that different. The average values aren't that different as well, so we actually wouldn't suspect too much of an association going on. It doesn't look like, knowing the class level of the individual really narrows down what that typical value for the height would be. So here we don't see very big differences, but when the typical values do look very different, that indicates a stronger and stronger and more practically significant association going on. All right, so we scan the side-by-side box plots just to see how different they are, and then we really make the assessment of, what are we actually comparing? Are we comparing averages, or are we comparing medians? Basically, is the distribution of y values for each level of x, well described by a normal curve, or is that not the case? And so here are the QQ plots that we focus in on. If the QQ plots look good, and looking good means the points are inside the upper and lower dotted bands, with the possible exception of a few points on the very far left or the far right. If that's the case, then the QQ plots look good, and the overall distribution of y looks like a normal distribution, that bell-shaped curve. if we see systematic deviations away from those upper and lower dotted bands, then we know we need to be comparing medians because the normal distribution is no longer a good description of the distribution of y values. So here's what I mean. Here's a histogram of a distribution of y, and we see that it looks, kind of like a normal curve here. And indeed, looking at the QQ plot, those points are inside the upper and lower dotted bands. This distribution is very obviously quite skewed, and that's reflected in this systematic bend in the QQ plot. The points aren't matching up to that diagonal line, and they're kind of going away from the upper and lower dotted bands, not only on the left and right-hand portions, but also in the middle. There's a systematic deviation. So I'd be okay comparing averages if all the QQ plots look like this. I'd have to compare medians if the QQ plots look like that. Okay, so that's what we're comparing. We're comparing the difference in averages, or the difference in medians, between each level of x. And since we are just collecting data here, we never expect those averages or medians to match up exactly for each level of x. We expect some variability. So our test is going to look to see if the variability observed is something that can be readily explainable by chance, or if an association is a better explanation. And so the ANOVA test is the test we use when we look at differences in averages. And what that does is it comes up with a measure for how different the averages are between the levels of x, and it compares that to the difference that we would expect to see if there was no association. And so that's what the ANOVA is, comparing the observed variability in averages to the expected variability if x and y were independent. If we're comparing medians instead, well, we do the median test. And instead what we do is we look at the fraction of y values for each level of x that are above or below the overall median in the data. And if there was no association going on, then we would expect for each level of x for it to be about 50% of those values to be above or below the overall median. And so it compares basically the fraction of values that are above and below the median to 50% here. If there's too big of a difference, that's evidence there's an association going on, that the medians are somehow different between the levels of x. So once the test is performed, once we've measured what we need to measure, and once we've figured out what kinds of values we would expect to see by chance, we measure the p-value of the association, basically the probability that chance alone could give you a discrepancy in averages or discrepancy in medians here, at least as big as what you collected in your data. So how do we know what values of the discrepancy in averages or discrepancy in medians can be found by chance? Well, we run that permutation procedure by randomly pairing together x and y values and seeing what the discrepancy in averages or discrepancy in medians actually are. All right, so that's the definition of the p-value. Basically, when we do the permutation procedure, we look at the fraction of those permutation data sets where x and y have no association, and look at the fraction of them that produce discrepancies in averages or medians at least as big as what we've observed in the data. By definition, that's our p-value, the probability of getting at least as large a discrepancy by chance alone. So if it's less than 5%, we say the association is statistically significant. If it's 5% or larger, the association is not statistically significant. And once again, just like all p-values, getting a statistically significant association doesn't mean that it's strong. We need to look at the side-by-side box plots for that. And it doesn't mean that it's interesting at all. That's given to you by the context of the problem. And also, when we don't find a statistically significant association, that doesn't mean that there's no relationship going on. It just means that if there is, it's too weak to be detected, or perhaps there's a lurking variable involved that's suppressing the association, making us unable to detect it from our data. So when we run the command associate, we're presented with the averages for each level of x here. In this case, we're looking at whether or not there's an association between someone's self-assessed rating of attractiveness, the y variable, and whether or not they have a significant other, either yes or no. And so looking at the averages for each group, we see that there's a relatively small difference in average, 2.62 here. And we'd like to know, can chance alone just produce that big of a discrepancy? Well, the p-value in this case is 4.6%, the estimated p-value. And in this case, the test is inconclusive because based on the 95% confidence interval, I'm not sure if the p-value is less than 5% or bigger than 5%. So if it's the right thing to do to compare averages, the typical value of y being well summarized by the average, then based on the results of this, we're not exactly sure if the association is statistically significant. We're not sure if this difference in averages can be readily explainable by chance, or if the better explanation is that there is an association going on. If instead we were actually comparing medians between the two groups, and that just depends on what the QQ plots look like. Well, we actually see the medians being identical here, so there's no difference in medians. There's no association going on in that case. So the conclusion depends on which measure we're choosing to compare, which is told to us by what the distributions look like. In other words, do they look like a normal distribution based on that QQ plot or not? All right, and the last case is how do we analyze the association with both variables are numerical quantitative variables? What do you need to be able to do? Well, given a scatter plot, you need to be able to talk intelligently about it. Describe that stream of points. Tell me about its direction, form, and any unusual features you might see. And since we do want to do an analysis of an association, we've talked about two ways of measuring the strength of that association with Spearman's correlation, or Spearman's rank correlation, or Pearson's correlation R. And there are some relationships where we can't use either to actually do it. So be able to pick out which of those two measures, if either of them are appropriate for measuring the strength and for the test of significance. So also one thing we explored a little bit with that core demo was what the effect of adding an outlier to a plot will do. We've seen how an outlier can induce a strong correlation when otherwise there really isn't one. We've seen how an outlier can destroy an otherwise very strong relationship between x and y. So be able to anticipate what would happen to a correlation if I were to add, say, an additional point to a plot. And we've already touched upon this. We've talked about the difference between two variables having a correlation and two variables having an association. Make sure you're clear on the difference. And also make sure that you're very clear that just because there is a statistically significant correlation or association going on, that never establishes that there's a cause and effect association going on between the two variables. Changing an individual's x value doesn't necessarily cause their y value to change. The statistical analysis doesn't establish a physical law. It only makes a comment on, what the overall trends are when you compare individuals. So when we do choose which measure of the strength we're going to be using, Pearson's correlation R or Spearman's rank correlation, we know that we can interpret Pearson's correlation R by squaring it. So be able to interpret the squared value of the correlation and tell us what that means in the context of the problem. And then when we run the statistical test, make sure that you can interpret what the p-value of the association is actually telling us. What's it a direct comment on? And how is it estimated? How does that permutation procedure work? And how do we use it to gauge statistical significance? So very brief review, given some scatter plots here, we talk about the direction of the relationship either being positive when the stream is going up and to the right, or negative when it's going down and to the right. And it doesn't matter if there's any sort of curvature, as long as the overall trajectory is, always consistently positive, we say that it's a positive relationship. Not all relationships are just uniformly negative or uniformly positive here. Here we actually have a mix of positive and negative directions. The next thing we talk about is the form. Is the trajectory of the stream of points well described by a straight line, like what we see here and here, or is there some sort of curvature to the trajectory? So these two plots show curvature, implying the relationship is non-linear between x and y. And there are two types of nonlinearities. We have monotonic nonlinearity, where the direction is either all positive or all negative, and non-monotonic nonlinearities, where there's a mix of positive and negative parts. All right, we also talk about the strength of the relationship based on how much scatter there is in the scatter plot. And basically, the more vertical scatter, the weaker that relationship is. This relationship is extremely strong because there's not much scatter around the trajectory. Once I know the individual's value of x, that's narrowed down greatly what the possible values of y that, might happen. If x is 0, individuals' y values are right at about 1. If x is 0.5, individuals' y values are right at about 1.4. This is a very weak or non-existent relationship because I see that, all right, if I look at individuals with an x of 3, the y values are between about 8 and 12. And if I look at individuals with x of 5, well, the y values are still between 8 and 12, knowing x didn't narrow down the possible values for y. Okay, the last thing that we look at is the existence of any unusual features. And these are key in determining, which measure of association I'm going to use to summarize its strength. So we look for heteroscedasticity, where the vertical spread in the y values is smaller for some values of x and larger for some values of x. We see that here, and we see that here. And we look for outliers, points that are very different from the overall stream here. All right, so our two measures of correlation here, Pearson's correlation and Spearman's rank correlation, are appropriate depending on what the plot looks like. So if that plot is well described by kind of an ellipse, like what we see here or what we see here, that's when we use Pearson's correlation. If it doesn't look like an ellipse, if it has heteroscedasticity, if it has outliers, as long as the trajectory is monotonic, that's when we use Pearson's rank correlation. So if we're going to use Pearson's correlation coefficient r, what does that tell us? Well, the values of r are between -1 and 1, and the sign matches up with the direction of the relationship. The important thing to know here is that the farther that r is from 0, either positive or negative, the stronger that relationship actually is. And a value of r of 0 means that there's no linear component to the relationship. Remember, Pearson's correlation coefficient is only appropriate for describing scatter plots whose trajectories are well summarized by a straight line. And so an r of 0 doesn't mean that there's no association going on, just that there's no linear component to that association. So we've talked about correlation versus association. I'm going to skip this slide and talk about what different correlations look like. So all four of these cases, the stream of points looks well summarized by an ellipse. And you'll notice that the point clouds that have less scatter have larger values away from 0 for the correlation. So a correlation of 0.9 looks like this. Correlation of 0.3, still kind of looks like an amorphous blob. These four examples have correlations equal to 0, but there's still a very obvious strong association going on. Once I know an individual's x value, I've narrowed down what the possible y values are. But the reason the correlations are 0 here is because there's no linear component to these relationships. These are all non-linear relationships, and they can't be measured in terms of strength with Pearson's correlation. All right, so to interpret the value of r, we actually square it. That's called the coefficient determination, and it tells us something about how much variation in individuals' y values can be attributed to the difference in the x values. So what we've said is that the percentage of the variation in the individual's y values in the data set that can be attributed to differences in the individual's x values, that's what we're referring to as r squared. And the other way to think about it is that, informally, if I know an individual's value of x, that essentially gets me r squared of the way there to knowing their value of y for whatever reason. Not a cause and effect sort of thing going on, but there just happens to be a relationship there. All right, so the larger the value of r squared, and r squared can go up to 100% here, essentially the stronger that correlation is. But also one of the key things is that just because this is a very large r squared doesn't mean that correlation is actually an appropriate measure for describing that relationship. You can have very strong curved relationships, like the one we see right here, actually having a very, very large value of r squared, but we wouldn't want to use Pearson's correlation to measure the strength of this guy because of its curvature. All right, so larger values indicate stronger relationships. How large is, interesting? How large is important? Well, that's in the eye of the beholder. So I can't tell you what value of r squared is large and important. That's always going to be part of the context of the problem. So here's the example where we looked at the relationship between friendship potential of women and how attractive they were as gauged by mostly males. And if we looked at the correlation, we saw it was 0.75. It does a good job at describing the strength because the trajectory of points is linear. And when I square it, I get a value of 0.56, or 56%. So in other words, 56% of the variation in the y values, friendship potentials here, which range from 1.5 to 4, can be attributed to differences in the woman's attractiveness levels. Or in other words, knowing how attractive men typically view the woman gets me about 56% of the way there to knowing what the friendship potential of that woman is. The remainder, 44% of that variation, must be attributable to other factors. All right, so we've talked about in business analytics how we typically have very many variables, and we're interested in studying the correlations probably between every single pair. And so the correlation matrix was a quick way of kind of scanning through different pairs of variables to see what the correlations were. So this guy right here tells you the correlation between the attractiveness score and the facial symmetry score of individuals. And so it provides a nice, easy way to kind of look to see which variables are the most correlated. The ones along the diagonals don't mean anything because that's the correlation of fashion score with a variable with itself, obviously perfectly correlated, so we just ignore those. All right, so one of the big things we've talked about is just because a correlation might be statistically significant doesn't mean that there's a cause and effect relationship going on. or anything of that sort of nature, because very often quantities just happen to have a very strong correlation by chance. We looked at that with this website here where you picked out a spurious correlation. And other times there are lurking variables that are responsible for inducing the correlation between what you're measuring here. So there's actually a strong correlation between ice cream sales and death by sharks, not because it's a spurious one that just accidentally happened by chance, but actually one that's induced by the lurking variable, basically temperature. In the summer, people are out swimming and getting killed by sharks, and they're also buying sales more frequently. All right, so and that was one of the key things actually why we're introducing multiple regression is that correlations often exist because of lurking variables or something else that's really driving the positive or negative relationship going on. And so we never want to attribute cause and effect to the reason why we're observing some sort of correlation. So number of piercings and height has a strongly significant correlation. And it's a negative correlation, implying people with more height, taller people, tend to have fewer piercings. And the reason isn't cause and effect, it's due to the fact that we're looking at guys versus girls. Guys are typically taller and tend to have fewer piercings. Girls are shorter, tend to have more piercings. So we see this negative relationship going on between the height and the number of piercings. So really, to isolate any sort of an association or correlation of interest, we need to control for lurking variables. In other words, other reasons why there might be variation in individuals' y values. And that's where multiple regression actually came in. That's why we do multiple regression for descriptive modeling, is to control for the presence of lurking variables. We want to isolate or hone in on the relationship between a particular set of variables. All right, so how is the statistical test for a correlation or Spearman's rank correlation conducted? Well, it's the permutation procedure once again, where we take the observed values of x and y and we create a permutation data set just by randomly pairing together the observed values. And by design, the permutation data set has no relationship between the x and y values, so whatever value for r that you measured or whatever value for Spearman's rank correlation you measure is one that genuinely has happened by chance. So if you build up a collection of permutation data sets, you build up a collection of values of R or Spearman's rank correlation that have happened by chance, and you can compare what you observed in your data to those values. And we measure the p-value, basically the fraction of correlations in the permutation data sets that were at least as strong, in other words, at least as far from zero, either positive or negative, as the one you observed in your data. And so that p-value is essentially telling you, the probability of observing at least as strong a relationship just by random chance. X and y have no association. And so that's why we say the correlation is statistically significant if the p-value is less than 5%, because there's less than a 5% chance that a correlation at least as strong would have just magically occurred just by natural sampling variation. A better explanation is that there really is an association going on here. And also, once again, just because we have a statistically significant correlation, a very, very tiny p-value that never tells us whether or not that correlation is strong, we always have to check r squared, look at the scatter plot to see the strength or practical utility of any sort of correlation. All right, so I have a slide here that just illustrates how that permutation procedure works. Here are the original measured values of x and y. The permutation procedure randomly pairs the observed values of x and y together and measures the correlation, and does that again and again and again and again. Each of those values for the correlation in the permutation data sets are ones that have genuinely been produced by chance, so we can compare the value that we observed in our data to the values that happened by chance to get an idea of the probability of chance alone producing a correlation at least as big as what I have observed, at least as far from zero. All right, so once again, how do I choose between Pearson's correlation R and Spearman's rank correlation? It all has to do with the shape of the scatter plots. So it only makes sense to use Pearson's correlation when it makes sense to compare averages. And basically what that means is the shape of the scatter plot, shape of the stream of points, needs to look, roughly elliptical. The trajectory needs to be linear, and I have equal vertical spread, kind of as I scan from left to right. So Pearson's correlation, yes, for here. Pearson's correlation, no, for here, because I see heteroscedasticity. I see the vertical spread being small on the left, but big on the right. And here I see some outliers out here, which means that Pearson's correlation might be greatly affected by those points. So in this case, I'll use Spearman's rank correlation to measure the strength and to conduct the statistical tests. In Spearman's rank correlation, all it does is, instead of looking at the original values, converts those values into ranks. It basically says, okay, well, where's the biggest, second biggest, third biggest, etc. values of x, and just replace that with 1, 2, 3, 4, etc. do the same thing for y and actually find Pearson's correlation between the ranks. And the test proceeds the same way otherwise. So what we end up doing is, after running associate, we look at the values of Pearson's correlation and Spearman's rank correlation. We choose which one we're actually going to use to do the test based on the shape of that scatter plot. So Pearson's correlation, if that scatter plot looks elliptical and the trajectory is well described by a straight line, and Spearman's rank correlation otherwise, as long as the stream of points is monotonic. And in this case here, the values are not very large, they're very close to 0. And in fact, it doesn't really matter which one we're measuring. Both of these p-values are bigger than 5%, so we would say that the association is not statistically significant, in this case between the number of cell phone contacts that someone has and the percentage of fellow students that this person thinks is dateable. All right, so that is it for simple linear regression, or for associations. Next part is regression.